start covering stuff immediately. Okay, so first a quick reminder that this Friday, March 8th, is when registration opens for summer and fall classes. So if you go into SOAR and do class search or whatever, you can see what's being offered. Although not all of the instructor information is filled in yet for every class, but they're working on getting that in. So, and then so talk to your advisor about what to take and all that.
You talk to you.
Well, it's not always me, but I guess in most cases it is me. So, and then the source is only going to show like our regular courses, such as this one, not necessarily options like your research courses or thesis or dissertation. That would be in conjunction with your research advisor, who is also often me, but not necessarily me. Of course, at least there's no big rush. It's not like undergrad where you have to worry about classes filling up. So, okay, now we have everybody. Now, funny thing, I looked at what I absolutely needed to cover today. The method of steepest descent. That there's not much in terms of notes to get through. And I also have to be careful because some of the things that I would normally enjoy covering about this topic are assigned as homework problems. So I'll have to play that carefully. But what that means is we have a good amount of time today. If anybody has, I know at least one of you does, any homework questions? I know you have something, Kwesi. Oh. Okay. Never mind. I'm so embarrassed. Okay. So, all right, fine. Anybody else?
Ask us after Friday.
What?
Ask us after Friday.
And it's spring break.
Yeah, well.
Okay. Dang it. And I know I have some more quizzes that I still have to get through. Chapter 4. Also, for the first homework on Chapter 3, I know I have some of those turned in. Actually, let me take a look at that. Okay. 1, 2, 3, 4, 5. Now, I know I made that assignment optional, but if any of you have not turned it in but are intending to, please don't take much longer in doing that. So, because what I'd like to do is have all of them that I'm going to get in front of me, so I can go through and grade them all at once. Again, because I hate grading. So I don't want to have 2 stints of it for the same assignment. So, okay. Well, it looks like I have, a handful of quizzes to do. Well, what I might do, we'll see how it goes, because often I go off on tangents that end up chewing up lots of time. And that's why, well, there are 2 videos up, 2 video lectures. I did one on Monday, one on Tuesday. It took 5 attempts to get it right. So those are on the conclusion of Chapter 4. Those are on the lectures page now. They're under the February 25th and 27th lectures, just because that's when we would have had class if I had been here. Singular value decomposition and least squares of linear constraints. So you'll want to watch those before you do the homework problems on those sections. Okay, so seriously, no homework questions of any kind? Haven't started yet? What? What?
I've looked at it.
Okay, well that's
yeah. I mean, I've answered one question.
Okay, that's something.
Yes.
Okay, and I want to make clear that so this is something that applies all semester long, but certainly chapter 3, chapter 4 is a problem. And so for certain problems where you're asked to write a MATLAB function to solve ax equals b, like from chapter 3, or a least squares problem. So even if a problem simply says write a MATLAB function to do this, and generally it's something where it's described in pseudocode in some algorithm that's in the text, so you can go ahead and convert that into MATLAB. That it's important that you test it. So, for example, for a least squares problem, that's ax equals b, where A is not a square matrix. It has more rows than columns. So all right. So so for a least squares problem, to test it, so you create a matrix A, m by n. M has to be greater than n. So as an example, suppose I want to make a random matrix. Let's say 5 rows, 3 columns. So I could do that. So rand 5, 3. So number of rows, number of columns. And then I can make a B vector that has to have the same number of rows and 1 column. So that will be a column vector. Okay. And then, so now the interesting thing is, I've talked about with ax equals b in a square invertible case, in other words, chapter 3 stuff, use backslash. Well, it turns out that applies here too. So x equals a backslash b. So that works for any ax equals b problem. So what MATLAB does is it figures out, based on the a and b that you give it, what it would actually do. So I guess I'm spending first part of the class telling you about the wonders of backslash. So case 1, a is n by n and invertible. So that's Gaussian elimination. So I'm running GEPP, Gaussian elimination with partial pivoting. That's the most general approach to solving a square ax equals b system. And then it does the forward and back substitution after that to produce x. So in other words, PA equals LU, the LU decomposition with partial pivoting. So that's what it does in that case. Whereas if A is m by n, m greater than n, so then it's treating it as a least squares problem. So I honestly don't know. I'd have to look up, and maybe they don't have this information public. It can use the normal equations or the QR factorization. So now we're in chapter 4 stuff. So either one of those approaches to solve the problem in a least square sense. This also requires that A has full column rank. Otherwise, you have to use a different approach, which I haven't really talked about. And then finally, because this is a case where there's a unique solution. This is the case where ax equals b does not have a solution, but minimizing the norm of b minus ax, or residual vector, that does have a unique solution. And instead of a situation where A is, or a rank of A is strictly less than n. So in other words, A is rank deficient. The columns of A are not linearly independent. So for example, suppose A is m by n and m is strictly less than n. That would bring that situation about. But there are other possibilities, like even if it's a tall, thin matrix, m is greater than n again, but you still have linearly dependent columns. So anytime this happens, ax equals b can have may have infinitely many solutions. So what happens is you find the minimum norm solution to the least squares problem. So in other words, the norm of b minus ax is minimized. Now, in certain cases, that minimum may actually be 0. And to make a solution unique, the 2 norm of x itself is minimized. Okay. Now, I actually talk about this some in the lecture that I've recorded on the SVD. So if you've not watched that yet, I get into this case more there. Okay. And as for how it solves it in that case, it's really most likely a variant on the QR factorization. It's something that I didn't cover due to the rank deficiency. So again, I had to look up in MATLAB documentation which one it does in this case. I'm guessing a QR factorization because it has some advantageous properties. So QR in this case, and most likely in this case also. So that's what the very versatile backslash operator in MATLAB is doing. It's basically, that's why at Stanford, us graduate students were saying that solution of ax equals b is a backslash b in all numerical methods of propaganda. Because it's going to find x so that ax minus b is as small as possible. And in the case where that solution is not unique, it's going to find a one of minimum norm, so one that is regularized in some sense. Okay. So these are things you can use to, if you write a function, a MATLAB function for a homework problem that requires you to solve whatever ax equals b problem you have, you can use this to test it and check your solution. Okay. Now, other things you can test, like for example, I believe there were homework problems in chapter 4 where you're writing a function to do QR factorization, like using Gibbons rotations or household reflections. So for QR factorization, so to do A equals QR, what you do in MATLAB is this. QR is, Q comma R is equal to QR, this is lowercase, of A. And that will give you the full QR factorization. Now, the algorithms in the homework, like to compute QR factorization using Gibbons rotations or household reflections or Graham-Schmidt, will all produce the R. They do not necessarily produce the Q explicitly, although you can make them do that. Now for a full rank matrix, the QR factorization is unique. So the one that MATLAB produces using this ought to agree. Let's see. Actually, there's one possibility of a variation. That could happen, for example, if if you examine, like you may have like the signs of some entries being different, but other than that, so like for example, okay, you may have a situation where you look at the Q and the R from what you implemented and what MATLAB returns. What may happen is you might have columns of Q or rows of R, those entries having different signs than what you produced, because there can be slight differences in what like household reflections or Gibbons rotations can produce. But at least you're going to tell if you're in the ballpark, because if there's any disagreement other than that, you know that something went wrong. Also, if you just go ahead and you can generate your code generates a Q and an R, just multiply them together and check, does it equal the original A again? If not, you know you messed up. So there's all kinds of things like that. Well, like in chapter 3, there's a problem. I gave you a matrix, compute the LU decomposition by hand. Well, once you have an L and a U, go ahead and multiply them. Have MATLAB multiply them. And check if you recover the original A. So these are the things that's important to get in the habit of doing to when you write something. Go ahead and just perform a simple test like this to give you at least some confidence that your code is working. Like when I was a software engineer, for every level of code we had, in addition to writing the code itself, we wrote additional code whose sole purpose was to test every little function we had. Because what if we had to make a change to it? We had to make sure that it still works. So we have a zillion tests on hand so that we can be confident that at least this part of the code was not messing up. If something did go wrong, we know to look elsewhere. Like last time I taught Math 460, I actually wrote some MATLAB scripts that would grade the assignments, the MATLAB portions of the assignments, in an automated fashion. I made up a problem, I wrote a script that would call the students function, and I would know what the answer is supposed to be. I would check against that. So then I have a MATLAB script tell me in its output, okay, this answer agreed, so they get full points. This did not agree. And then I would look at it to see what grade to really give. But it's something that helped me, because at least I could confirm that certain things were right. So it's important not to be minimalist about these things, just because of what's stated in the problem. Because if you submit to me a MATLAB function to solve a certain problem, you're emailing me an M file, I'm going to run it. And if you go ahead and run it first, then at least you have a much better chance of making sure you get full points by the time I run it. Because there's some times when something's turned into me and I haven't even run it yet. I just open up the M file, look at it, and like, oh God, this is. Also the MATLAB editor, like if you look off to the right, like when you have an M file open, that there'll be a little square at the top right corner that's either green, red, or orange. So red is when you have syntax errors. Orange is when you have warnings, which may or may not be a big deal, it just depends. And then green is you're good to go. In other words, there are no syntax errors. Your code may still be completely wrong. So make sure it's clear about that. Because it doesn't care about the actual algorithm or what you're trying to solve. But, so, at least make sure it's orange. Don't turn it in if not, because that's just going to piss me off. You don't want me to be pissed off when I'm grading. More pissed off. Because I already will be just because I'm grading. These are habits that are important to build. Okay. All right. Well, I guess that probably took the equivalent amount of time as to what would have been given to homework questions. Okay. Now, yeah. So a number of you took. Well, actually, probably only a little more than half of you took Math 561, where after talking about solving AX equals B using Gaussian elimination, we spent some time talking about iterative methods for AX equals B. They were called the Jacobi, Gauss-Seidel, and SOR. Well, that knowledge is useless now because we're not going to talk about those iterative methods. I can talk about different iterative methods that I personally think are a lot more interesting. Because those methods are called stationary. Well, actually, so since I'm spending time on the other portion of the iterative methods chapter, it'd be a good idea to talk about iterative methods in general. Okay, because I spent a fair amount of time talking about Gaussian elimination and how it's a typical method used for the general case. So, why is Gaussian elimination in these certain cases a terrible idea? So, still worth covering, still very useful, but okay. So, suppose you have some knowledge about your particular problem, A equals B problem. Like, you might have an idea of what the approximate solution could be. Maybe you have like a good guess of a solution. Can't use it with Gaussian elimination. Gaussian elimination does not have any means of taking that extra knowledge into account. So it's very flexible that way. Another way in which Gaussian elimination is inflexible is, suppose you don't want the solution to full accuracy. It would be nice if you could expend less computational effort. You'll stop the process early. And yes, you get a solution that's less accurate, but you've also taken less time. Can't do that with Gaussian elimination either. Gaussian elimination is going to have to go from start to finish and produce a solution that is exact, except for whatever round-off error occurred. The thing is, sometimes there really is no point in getting that much accuracy, like a relative error on the order of 10 to the minus 15 or 16. Because what if your AX equals B problem has data in it, like the A and the B, that came from measurements? What if those measurements are not terribly accurate? Like maybe they're only accurate to within 1%. Therefore, your solution is not going to be very accurate either. So why spend a lot of time to compute a solution that's incredibly accurate for a model that's inaccurate? It's a waste of time. So, but Gaussian elimination doesn't allow you to do that. Okay. What if the matrix A is sparse? In other words, most of the entries are 0. Gaussian elimination, especially when pivoting is involved, can lead to fill-in. I mentioned this before when talking about banded matrices in particular, because those are sparse. But you also have some applications where the matrix is sparse and the non-zero entries are a bit more random. They're not necessarily contained within one band. They can be scattered about. And doing Gaussian elimination with pivoting can, actually even without pivoting in cases like that, can cause new non-zero entries to appear So solving x equals b becomes unreasonably inefficient. And then finally, you may not even have the matrix A explicitly. In other words, as a conventional two-dimensional array where you have stored all the entries aij, ij going from 1 to n. And that seems kind of crazy. Like, how are you going to solve ax equals b when you don't even have a matrix handy? But it's actually not unreasonable at all. You might have matrix A represented as a function, y equals f of x, which happens to compute the matrix vector product A times x. This is especially reasonable if A is a sparse matrix, where you don't really want to store A as a two-dimensional array anyway. So in this case, A is implicitly represented by this function f. Now, if you have that, you could get A explicitly by calling f on each standard basis vector. Like, you pass in E1, E2, E3 to get A column by column. But that takes a lot of time. So you may not really want to go to the trouble of doing that. So it'd be nice to have methods for solving ax equals b that only involve A through this operation, matrix vector product. And actually, all of the iterative methods that I'm going to cover in this class have that property. So that is possible. So there are a lot of compelling reasons to not use Gaussian elimination with whatever pivoting scheme. So what we do instead are iterative methods. Okay. And that is the subject of chapter 5. Now, yes, I'm sequestering my chocolate milk. Kidding, you can take some before you go. All right. Now, there are two classes of iterative methods. The first kind are stationary. This is covered in section 5.1. I spent time on these in Math 561 last spring. So therefore, I'm not bothering with them in this class. So these have an iteration that's of this form. So I'm using the superscript with parentheses to indicate an iterate. We're going to compute x1, x2, x3 for these superscripts that in the limit, as this index goes to infinity, should converge to the exact solution. Equal to nx k plus b, where a is equal to m minus n. And there are different combinations of m and n that lead to different stationary iterative methods, Jacobi, Gauss-Seidel, SOR. And it's called stationary because this is what's called a fixed point iteration, where the limit x is a stationary point, also known as a fixed point. And so there's a lot of theory in that that's actually covered in Math, actually it's supposed to be covered in Math 460, but last time it wasn't. Well, I'm teaching that in the fall, 460, 560. Maybe if you didn't take it last time around, you can. Okay. So the other class of iterative methods is what I will spend time on are the non-stationary. And okay, actually, 5.2, 5.3. So the rest of chapter 5. And these iterative methods all have this form where each new guess or iterate that's converging to the solution is equal to the previous one plus some constant that I'll call alpha k times some vector that I'll call pk. And this vector is called a search direction. So the idea is we have some initial guess, or maybe if we don't know how to guess, the initial guess might just be 0. And from our initial guess, we try to find some direction to go in n-dimensional space. And we figure out how far to go in that direction. That's this scaling factor alpha k to get our next guess. And then from there, we pick a new direction. So it's like we're searching through n-dimensional space for a solution to ax equals b. And there's different ways to come up with a helpful search direction and then whatever scaling factor. Okay. But they're all going to have this this kind of form. So as a starting point, I'm going to focus on a particular class of matrices, SPD, symmetric positive definite. So because the idea is with a symmetric positive definite matrix, you can come up with a minimization problem where the solution, the minimum, is achieved at x, the solution to ax equals b. So we're changing the system of linear equations to a minimization problem, and we can choose our search directions in such a way as to try to get closer to that minimum. So then we can use ideas from calculus. So that leads to the method I want to focus on today, or the rest of today. Method of steepest descents. Okay. So we're going to assume that A is symmetric, positive definite, or SPD. I can define this function 5x to be okay, 1/2 x transpose ax minus x transpose b for some given b. Okay. So what I'm going to do is try to minimize this function. Find the minimum of this function. Now, to find a minimum of this function, we need two things. We need the gradient of phi to be equal to the 0 vector. And then use the h sub phi In other words, the Hessian of phi, in other words, a matrix of second partial derivatives, needs to also be SPD, symmetric positive definite. So if we can find a point X where it's gradient is 0 and the Hessian is also the SPD at that point, we know we have a local minimum. So that's from multivariable calculus. Okay, so what is the gradient of this function? So what I'm going to do is write it out. I did something like this, similar to this for the least squares problem. But it's always good to look at these at an element by element level just to get used to the idea. So I'm going to rewrite 5x in terms of the entries of A, X, and B. So this expression, x transpose AX, is a sum over all I and j, so it's a double summation. Aij, xi, xj. So really, the Aij, xj part comes from A times x. So if I'm writing that out entry by entry, that's what I would get. And then, if I take the ith entry of AX and multiply it by xi, that's this dot product. It's dot product of x with AX. And that's what gives me this expression here. Actually, for clarity, I'm going to write it that way. So sum over I, xi, sum over j, aij, xj. So this is ax entry I. So now you can see dot product of x with ax. And then we have this term here. That's also a sum. Xi, bi. So it's just a dot product. Questions so far? So gradient to be 0, I need to take a partial derivative of this with respect to each x. So I'm just going to choose an index, k. I'll take a partial derivative with respect to xk. So a partial derivative of phi with respect to xk is equal to, so 1/2, so I'll have my sums. Now, I have two x's in here that are multiplied. And I also have a constant aij. That's going to call for product rule. So if I differentiate xi first, so that's going to be partial of xi with respect to xk times aijxj. And then for differentiating the xj, I'm going to have xi, aij, partial of xj with respect to xk. And then I have the other term, minus sum, partial of xi with respect to xk times bi. Okay. So the only derivatives I have in here are derivatives of some x with respect to a different x. So let's take this one, for example, partial of xi with respect to xk. What can that possibly be equal to? Keep in mind, all the x's are independent variables. Zero, except when?
When they equal each other.
Yeah, in which case it's
1.
Yeah, so it's 1 or 0. Or, very concisely, it's delta ik, Kronecker delta, which is equal to 1 if I is equal to k, and 0 otherwise. Okay. So, I'll break this up into two sums. So for this part, this is 1 only if I is equal to k. So the sum over I is going to go away. There's only one term sticks around. So I'm going to have I equal k. So I have a kj xj for this part. And then for the other part, here j must equal k. So the sum over j is going to go away. I still have the sum over I. So I have xi a I k. And then over here, same situation, I must equal k. So all I have here is bk. So all the other terms will disappear. Okay. All right. This is matrix vector product. So I have 1/2 times ax element k. So that's just comes right off the formula for matrix vector product. Here, it's almost a matrix vector product. Notice here the second index of akj matches the index of x. Not so here. The first index of aik matches the index of x. So it's not ax. What? Yes. That's what I was hoping I was hearing. Yeah. A transpose. But what do we know about A? Symmetric.
Symmetric function.
So it is ax. That's why we have a 1/2. Now these terms combine. It's just ax minus bk. So this one partial derivative with respect to xk is a kth component of ax minus b. So in other words, the gradient of phi of x is equal to ax minus b. So this is quite convenient because we want this to equal 0. So the one and only critical point is the solution of ax equals b. Okay. Now, we don't know yet if this one critical point is a local max or a local min, or it's multivariable, so it could be a saddle point, or it could be none of these things. So to be sure, we need the Hessian, and that comes from taking the second partial derivatives. So you're going to be taking all the partial derivatives of this with respect to all the x's. But if you do that, you won't get anything from here because b is a constant. Also, this is a linear function of x. So like if you take a derivative of ax, you get a. So when you take derivatives of this with respect to sub x, you're just going to get entries of a. So I'll just cut to the chase here, that the Hessian of phi is just a. So if you carried out the partial differentiation, you'd see that's what you get. But a is assumed to be symmetric positive definite. So this x that solves ax equals b is a local minimum. In fact, it can be shown that it is a, although of course we know it's unique because ax equals b has a unique solution. So it's actually the global minimizer of this function. We can solve ax equals b for this kind of system, symmetric positive definite, by any approach that we might use to minimize a function like this phi. So an optimization is a whole field in itself. Well, we have a class on it, but it's rarely offered, unfortunately. Math 519. But this summer we're offering 518. Just missed. So that's all about, it's a whole semester of finding minimums of functions in different ways. So any of those techniques could be used on a function like this. So what I'm going to do is show you one such technique that's useful for a function like this that has this unique minimum at x, and we're going to get an iterative method out of it. Now, the main idea behind this iterative method also comes from multivariable calculus. And that is, for any function phi, the gradient of phi. Now, a gradient is a vector. It's a vector consisting of all of the first partial derivatives of your function. The gradient indicates the direction of steepest ascent. In other words, from that point x, if you compute the gradient, then that direction that the gradient vector is pointing in is a direction in which a function is increasing most rapidly. So what that means is negative phi is a direction of steepest descent. And that's what we're going to use here because we're trying to minimize phi. So if we have some initial guess, whatever that might be, and we plug it into phi, then we like to reduce its value as much as possible. So minus the gradient of phi is a negative of this, so it's b minus ax. What do we call this vector? We've given it a name from talking about least squares problems. Or actually even before that. B minus AX. Yeah, it's also what came up on the quiz. So the residual is the direction of steepest descent. Now, that by itself doesn't help you unless you know that minimizing phi solves AX equals B. Now, in the case of A being symmetric positive definite, I've just shown you that it does. But if A is not SPD, we don't know that we're getting a minimum out of it. So the assumption that A is symmetric positive definite is essential for all this. So in other words, from whatever x we're starting at, if we use this direction, a direction of steepest descent, as a search direction, then we know we're making progress towards minimizing towards minimizing phi, and therefore making progress towards solving AX equals B. So here's what we can do. I could give like a skeleton of an algorithm, but so certain details will still need to be filled in. So I'm going to choose some initial guess as my solution. Now, if I have no idea how to guess, I'll just choose 0. So then I'll start a loop. And within this loop, what I'll do is I'll compute my direction of steepest descent, the residual, and I'll call it RK. So that's this vector here, B minus A xk. So this is a direction that I'll be wandering away from xk from to try to find a better x. Okay. So then I will set my new x, xk plus 1, to be xk plus some constant, alpha k, times rk. And that's my skeleton algorithm. So the idea is, I know that if I travel in this direction, I will make some progress towards making the value of phi smaller. And so I'll travel that direction to get my new x. I'll compute my new direction of steepest descent and travel in that direction from there. So presumably, doing this, I can make progress towards minimizing phi, therefore solving ax equals b. Now, there's one really important detail I've left out here. What's incomplete about this idea? What is unknown? What?
The constant, like where it came from.
Yeah, alpha k. I've told you nothing about how to choose that. Kind of important. So we know what direction to go in. We have no idea how far to go in that direction to ensure that we're actually making as much progress as possible. So this is our literal question mark. So now let's tackle that. We need a way of choosing that makes sense. So the idea is, I've already stipulated that my new x is going to have this form. I just need to choose this constant. So all you do is choose alpha k so that phi evaluated at my new x, xk plus 1, which is equal to phi of xk plus alpha k rk, is minimized. Because that is my goal, to minimize phi. The thing is, my overall goal is to minimize phi on the whole space, all of Rn. But now I'm not doing that. I'm solving a smaller scale minimization problem because everything in this argument is known except alpha k. So I can think of this as a function. I'll call it g of alpha k. So I really want to find a minimum of that. I'm trying to find the smallest value of phi among all inputs of this form. I'm restricting myself. In other words, I've reduced an n-dimensional minimization problem to a one-dimensional minimization problem. So it's a Cal1 problem. So if I think of this as a function that's depending only on alpha k, function of one variable, I can follow the procedure from Cal1. Take the derivative, set it equal to 0. Hopefully the second derivative is positive for a local min, and so forth. So that's what we're going to do. We're going to solve this Cal1 problem. But it's not something you'd really want to give to a Cal1 student, because it's kind of messy. Right? That's what higher level math is. It's a carefully crafted selection of lower level homework problems. And that's what makes it such a pain, is that how they're strung together. Plus the details are just literally mind-blowing. Okay, so I'm going to write out what this function is, g of alpha k. So it's equal to this, phi of all this. So that would be 1/2 times this vector, xk plus alpha k rk, transpose a times the same thing, minus, okay, B transpose that same vector. All right. Now, all right, what I'll do is, actually, no, I'm not going to do that. I was going to FOIL all this out, but that's really unnecessary. So G prime of alpha K. So I'm going to take a derivative of this with respect to alpha K. So I have a bunch of things multiplied together, so I'm going to use the product rule. But keep in mind, A is a constant matrix, so we treat that as a constant. So first term, I take a derivative of just this part. So it's 1/2 RK transpose A times all the rest of this. Plus, now I leave this alone. Oh, 4 pieces. That makes me 4/7 of a Jedi. Okay. Now, so now I'm going to leave this term alone. Xk plus alpha K RK transpose A, and then I take a derivative of this, and that will again be RK. And then I take a derivative of this part. So it's minus B transpose, and the derivative of this is again RK. Make sure I'm not missing anything. Okay. All right, that's kind of ugly. Now, if we use the fact that A is symmetric and the dot product of real vectors is commutative, I can actually combine these two terms. So if I think of it this way, A is equal to A transpose. So this is ARK transpose, which is, I have ARK over here. So let's combine these two. So I have 1/2 XK plus, actually, no, the other way is better. I don't want the 1/2 either, by combining them. And I can distribute A through here. AXK plus alpha K ARK. Right? And then I have minus B transpose RK. Now, because the dot product is commutative, I can swap these two. So I'm going to put RK first and B second. And the reason I'm doing that is now I have RK first in both dot products. So I can factor that out. So I have RK transpose, and what's left is AXK plus alpha K ARK minus B. Now, I want this to equal 0, so I'm trying to find a minimum. So now I'm setting this equal to 0, so I'm going to move some terms to the other side. So this term, I'm going to leave where it is. So I have alpha k, and then I have rk transpose ark, and that must be equal to rk transpose, and I have b that gets moved to the other side, so now it's a plus. And then this is moved to the other side, so that's a minus. Okay. So now I have this equation for alpha, k, which I can solve. But before I do, I can simplify that a little bit. Can anyone see what could be simplified? Or at least written more concisely. Based on what's written on the board. Yeah, that. That's RK. So that is RK transpose RK. So alpha K times this is equal to this. So now I just divide by this. And I get alpha K. So now I have the elusive parameter alpha K. So alpha K is equal to RK transpose RK over RK transpose ARK. So mystery solved. So if I choose alpha K to be equal to that, then xk plus 1 is the best choice for going in that direction in terms of minimizing phi along that direction. And once I have my xk plus 1, then I go back up here, get the new steepest descent direction, and I just repeat this whole process. Any questions about what happened here? What? Okay.
Huh?
What?
It's gonna take me
Okay. Well, anybody about any manipulations that were too mysterious? Or? Can anyone tell me, how come we don't have to worry about dividing by 0 here? Because we're dividing by this expression, RK transpose ARK. How do we know that that's not going to be 0? Yeah, the definition of SPD is that for any non-zero vector, this is strictly positive. And if RK was 0, we'd be done anyway, because we'd have the exact solution. So we don't have to worry about dividing by 0 in that case. But it's another reason why the assumption that A is SPD is critical, because otherwise we couldn't be sure of that. Okay. So this whole thing, this algorithm, with this included, is called the method of steepest descent. So your first non-stationary iterative method. Yeah. So actually coming up with this parameter value is one of the explorations in this section, so I won't be assigning that one. Okay.
And you could accidentally assign it.
What?
You can still assign
Accidentally
it.
assign it.
Well, in that case, you really better be able to do it.
Yeah.
Okay.
Confidence booster.
All right. What?
Test our knowledge.
Or note taking skills.
Test your regurgitation skills.
Hey, you want to know something?
Exactly.
That is important.
Okay. All right.
Very
I'm going to take
critical
away my
students.
speech about things about students.
Now, there is one interesting property of steepest descent that is also assigned as an exploration, and I will assign it, so I'm not going to work it out here, I'm like not above giving a hint. Okay. So property of steepest descent is that each residual RK is perpendicular to the previous one. So in other words, RK transpose RK minus 1 is 0. So will be one of the homework problems. I haven't posted on the site yet. We're still working on chapter 4 anyway. To actually work out this inner product and show that it is 0. So, and a way you can do that is you can express RK. Now, RK is already defined in terms of xk. Therefore, that gives you a way of expressing it in terms of xk minus 1, which in turn allows you to express it in terms of rk minus 1. So once you keep substituting based on all the definitions given in the algorithm itself, you can get yourself down to an expression where you can actually show that you can see for yourself that it's equal to 0 through lots of things magically canceling out. So it's not a terribly involved proof, but I wouldn't call it trivial either. Right.
Good stopping point.
What? Oh,
You can
actually,
make that problem hard by making it fill in the blank.
But the whole solution's on video.
That's
Yeah.
just an extra bonus.
Yeah. Well, actually, yeah, I worked out that problem at the bottom of this page. So, the point is, it doesn't take very many lines to do. So,
I'll distract him at the end of class. Someone steal the page.
I can eat it like some people do.
Please don't.
Yeah, we're better off with chocolate milk. Okay. Now, this makes sense in that you want the algorithm to work this way just because if you're already going down a certain direction and finding the best value along that direction, then the next direction ought to be completely independent of it. So you're really exploring new territory. So this makes sense. But the problem is this is not enough. So in another exploration that I will assign, calls for implementing this in MATLAB. And I give a couple of matrices to try it out on. So for one of them, it's going to work well, and the other, it's not, which you probably could have predicted without me telling you, because all homework problems are contrived that way. Because what happens is the matrices involved in the problem, they're both 2 by 2. So if you're working in the R2, so two-dimensional space, you really should only need to consider 2 different directions. And then, bam, you're at the solution. But it's not what happens. Because, all right, so each direction is perpendicular to the previous one. So we might have a situation like this, like RK, and that's perpendicular to RK minus 1. So now you're going to pick RK plus 1. So suppose we're in 2-dimensional space. In other words, we're on the board. You pick RK plus 1. That's equal in direction to RK minus 1. In other words, you zigzag. So, so that's what happens if you try this method of steepest descent in a 2-dimensional situation, that you're not going to converge to a solution in 2 steps. You're going to keep zigzagging. Now, and actually you can tell what's going to happen by considering the graph of a function phi. It's a surface. So if a matrix is well conditioned, then if you look at the graph of a surface phi, you can think of it as like a nice bowl, has a clearly defined minimum, and there's not, the zigzagging is not bad. So you can get pretty close to a solution in not too many steps. So you make good progress each time, even though there's a zigzag to it. If the matrix is ill-conditioned, then the instead of a bowl, it's more like a really weird gravy boat. The level curves are really stretched out. Yeah, the level curves are really long, like hyperellipsoids. So you actually make very little progress towards a solution each step. So it zigzags and takes tiny steps. So it's like, and the thing is, I actually have a demo of this in MATLAB. It actually gets worse as you keep going. The steps get smaller and smaller. You feel like your xk is crawling towards the solution, the exact solution, and you feel like it's never going to get there. So having each search direction being, in some sense, completely independent of previous search directions is a highly desirable property for these kind of non-stationary iterative methods to have. And steepest descent just doesn't have it. So it's a starting point, but it definitely needs improvement. And that's what leads to the next iterative method that I'm going to cover, which will have to wait until after spring break, by which time you'll have forgotten all of this, or maybe forgotten everything I've covered this semester. Where the idea is, like, what we really like to do is have each search direction orthogonal to all previous search directions. Unfortunately, that's not practical to achieve. But what can be done is, if you can at least make each residual orthogonal to all previous residuals, and that leads to an algorithm known as the Lanczos algorithm. So I'd actually cover that first. But the thing is, now the residuals are no longer the search directions. The search directions actually would involve a linear combination of the residual and the previous search direction. So the search directions are not orthogonal, but they can be made orthogonal in a different sense. It's actually called a-orthogonal. So at least they're independent of each other. They're just not perpendicular. And that leads to a method called the conjugate gradient method, which is probably the most famous iterative method amongst only four symmetric positive definite systems. It's such a famous iterative method that they threw a party for its 50th birthday. So it was invented in 1952. So in 2002, they
Had cake.
they threw a bash, and it was we'll see. That was also my advisor Gene Gollum's 70th birthday, so they let him get in on a celebration. And it was held in Europe, so I didn't have a chance to go. So yeah. But the conjugate gradient method is quite effective. So it's very much used in real-world applications. Now, again, it's only for SPD, but there are variations of it that I'll discuss also the week after spring break that allow ideas from it to be used for unsymmetric matrices. So the interesting thing is, while there are these variations out there, they're still not that great. You don't really get the same effectiveness as you do for conjugate gradient in the SPD case. And Gene had a very interesting idea to pursue about how to use ideas from conjugate gradient for unsymmetric matrices. He thought of the idea in 2007 for an interesting application, computing the scattering amplitude of waves. So, for instance, radar bouncing off a aircraft. So this is important for the design of stealth planes. And so he had me come over to his house. We're going to work on a funding proposal together, and he showed me this idea that he'd just come up with on how to do it. And that was on November 6th of 2007. And I remember the date because 10 days after that, he passed away. Um, so, um, and the thing is, so we never got a chance to look into this. And so all I had was this piece of paper that he had written on with his idea. And I didn't really understand the full meaning behind it because it's not really my field. But I went to some conferences during the following year with numerical linear algebra people and people who knew Gene, and I showed this to them, and they're like, "Oh, okay, but there's something interesting to it." And so I actually had some of you know Amber Sumner look into this for her master's thesis. And there's some interesting things going on, but it's an extremely difficult problem to take his idea and make it into a fully functioning method. So she ended up doing something else for her doctoral dissertation. But it's something that I've always wanted to return to, and maybe she might want to also. Now there's no longer pressure of having to finish a PhD in a short timeline, but yeah, it's an interesting problem. Work has been done on conjugate gradient-like methods, but it all starts with steepest descent. That you're using this geometric idea to solve AX equals B, and then you find, okay, it doesn't work that well, and how do you fix it? And so it's been fixed quite well for the SPD case, and now how do you get it to work beyond that? So it's still a very active area of research to develop these kind of methods and get them to work more effectively for certain cases. So, and it's a fun area to look at. So, okay, so that concludes story time. And we only have 5 minutes left, but at least I covered this topic. So it'll be almost 2 weeks until I see a lot of you again. So see what happens with homework 4. We can spend any time on that during spring break. So, and then bring your questions about that on, a week from Monday.